All right, gentlemen. So today our panel will be about AI factories, design, power, and cooling dynamics. Joining me on this panel is first Mr. George Berbari, CEO of DC Pro, joining us with more than 40 years of experience and the pioneer of district cooling in the region, and the energy specialist and data center specialist. Followed by Mr. Scollay, with more than 30 years of experience as well across 3 continents and currently heading the data center director in DO. Mr. Stuart Mark, or Mark Stewart? Mr. Mark is joining us from Europe as well, and he's director of business also in George Fisher. And Mr. Ammar Horani, with 25 years of experience as well in the business, and he has played pioneer roles on different sides of the business, all the way from consultancy to system integrators and end user, and now he's spearheading the business for Eaton across the region. And myself, I'm Homere Debs, and I'm the business development director from Uptime Institute. So, it would be considered conservative to say that we are living today in the rise of AI. The AI applications and deployment and development and the AI adoption are all currently business driven, but all of those are practically housed within AI factories. So if we look at the global outlook of the plant capacities of the AI factories, we can see a huge 327 gigawatt to be planned till 2030. That's in 5 years from now. All right. So this business is mainly led through the North Americas, followed by South Asia Pac. And however, the rising star of this business is the Middle East and the GCC, with one of the biggest deployments that are happening across the globe. So above capacity start looking staggering and huge compared to the traditional loads that we have been used to it. And this all can be traced back to the AI workloads and the computational load that is required in order to serve the AI models. And this can only be happening by using the power-hungry technologies of the GPUs versus the CPUs that we are used to. So this scale-up from GPU is actually propagating throughout the MEP infrastructure serving the IT load and so on. So the first question will go to Mr. Berbari. As AI capacities are driving the load of the rack loads very high, what are the design considerations that are being taken into consideration in order to cater for these loads?
For people who are having side discussion, gentlemen, can I request you to leave the room? Hello? Side discussion people. Can we have your attention? Hello? Please, if you want to talk, please talk outside. If you want to listen to us, please stay. We welcome you. Just a small thing. Now,
can I stay?
For sure you can stay. Most welcome. Now, since we have your attention, you know we are in a very transition stage in terms of chip development. This is driven by NVIDIA, AMD, Intel developing the chip. The current chip still is not encouraging energy efficiency. They want to use liquid-to-chip cooling, but we are still using chilled water. So right now, I mean, if you see Khazna developing in Ajman, a data center, I will release a little bit of confidential information. We are putting chilled water system. They are putting chilled water system supplied at 19 degree, return 23 degree. They are using propylene glycol on the secondary side, supplying 23 degrees C, and the return is 33 degrees C. the 10-degree delta T on the secondary side because of the limited piping space to the ship. So they want to reduce the flow. Now the ship itself is 17 to 20 degrees higher than the 33. So it's operating at 50. And we are not in a freezing country. Why are we using propylene glycol here? They said because it's inhibited, it has rust inhibitors, it's very similar to water in terms of behavior, and 3, it is stable and it doesn't resolve microbiological growth, it deters it, slow it down. So it's multiple solutions. So now, whatever happening in the US, NVIDIA work with Nalco on research, they brought it here, and they are driving the market with this. Now, will a ship be developed soon that will take 70, 80 degree, and we will be able to avoid compression cooling without chilled water? We are in this transition phase. But till now, I mean, we need that. And we're still seeing our design, we need, okay, if we use water cooled, we have a 1.5 multiplier on operation side, but on design side, we are reaching 1.7, 1.9 multiplier to the IT as connected load. And luckily, UAE is ahead, is building power excess to what they need. If you know, in Abu Dhabi, that Stargate project, they are building, in a year it will be ready, 1,200 megawatt power plant with solar as standby. So this is my conclusion. I mean, we are in that phase. That I hope that answer what we are going to. We are, as consultant, we are driven by the ship manufacturer. So we are responding to them. We are not driving. They are the drivers. We are the responders.
Thank you, Mr. George, for your inputs. Mr. Russ, I would like actually to address you when it comes to the AI factories. What are the actual expectations from resiliency perspective and requirements for the AI factories? Are we talking about the sweet spot of the tier 3 concurrently maintainable, or are we talking about something more or less? Well, I would like to hear your thoughts on this.
Okay, so I need some of George's magic again.
He wants to shout at them.
The question is, what levels of resiliency, operational support for these AI factories?
Yeah, so practically, what is the expectations out of AI factories when it comes to resiliency perspective? So are we talking about something like in collocation, like tier 3 plus or minus? What is it exactly for you?
I think the base expectation is still tier 3 in the sense that everybody wants and expects and probably needs concurrent maintainability. You have to be able to hot swap. We recently did I don't know, maybe it's a small AI factory. It was only 4,000 H100 GPUs. So that's a 5 megawatt deployment, which doesn't reach the kind of gigawatt and the gigabrags that we're hearing a lot. But it's a real deployment that we've done, and we've published it. So it's, I can say that without breaking confidentiality. What I've seen on that project and what I've seen on other projects is that speed is really trumping everything else. And so it's not that people are going to be cutting corners, but there's, the priority is, we've got, the GPUs are being produced incredibly fast, and there's new GPUs being produced all the time. The total number of H100 and H200s that were produced by NVIDIA reaches to something like 7 or 8 gigawatts, according to some data that I saw. And I would believe it, right? So within a very short space of time, they've produced 7 or 8 gigawatts worth of compute that's got to go somewhere. And the people who are buying that are not going to hang around and wait. They really, really need that to go live as quickly as possible because they need to operationalize their business. They need to make business returns out of that. They need to do something with it, basically. And they're not going to wait for the next GPU to come out and wait for 2 years, which is the kind of cycle we would have seen previously. Up until 2022 or something, you would have seen like a large deal of that nature, and people are willing to wait 18 months realistically and say, okay, you're going to build something and we'll do it properly and we'll do it right and it will take time. So that point I'm making is that the speed is probably changing some of these things, and it depends on the scale as well. So like I'll be in Texas next week, and we're going to see some of these like mega campuses that are hundreds of megawatts and gigawatts, and they're using completely revolutionary designs that we might see here. We've seen Stargate going live here, which is a similar copy of the Stargate that was done in Texas. So we will see different designs, and that will change necessarily. And the only last point I would make is when it comes to uptime. So if you are running a training workload and you need to turn it off, like that's part of the nature of the beast, actually. Even if I, as a data center provider, provide you with perfect 100% uptime, there will still be times when you need to turn it off and turn it down and up and down, and that's just how these things are run, as I understand it, which is a bit different from if you're running traditional IT or cloud services or hyperscale services, where being forced to turn something off is really a no-no, and ideally just doesn't happen unless it absolutely has to. And there's all sorts of processes and policies around when that can happen. So if you're running training, then there's going to be a little more flexibility, but anything that's built for training is going to end up as inferencing anyway. And anything which is GPU and liquid cooling is going to end up in the hands of hyperscalers one way or the other anyway. And so the industry will kind of morph from its existing state into this hybrid, I think, rather than a hot switch.
That is sure. I'm gonna get back to you as well on another aspect of the thing. So, with big data centers that we are hearing about, there's a lot, and like Mr. George has mentioned previously, there's a lot of liquid-based cooling systems that are being introduced, from direct-to-chip to immersion or cold plates and so on. So, how these new technologies introduced within these AI factories are impacting the management and operation of the data center on that front?
Yep.
Yes.
Yeah. So again, to talk to an example case we have, which has just gone live, and that's a 4,000 GPU supercluster. It's a single cluster. That's a big cluster, biggest in the Middle East probably at the current time. And what fascinated me about it when we went into that project, because I didn't have a lot of experience with this liquid cooling, none of us did, maybe up to a degree, was just how quickly we could turn to being able to say, yes, we can do that. And thanks to top quality consultants, engineers, all the technology is there. And operationalizing it isn't that hard, I would say. We've got a lot of pipes now. We have a lot of water pipes. So it's not some very similar operational policies that we had before, but we just need some different areas of focus. We need some different skill sets in the data center. We need some different people maybe. So we're going to have to tweak the types of people we have on shift and who's doing what. But it's not like a big wholesale change. We're not having to throw out a whole host of existing processes and procedures. The data center is not going to change that much. We've got traditional business running next door, and then this AI factory running, and all under the same roof essentially. So it's doable. I think the harder part, which we don't have to do because we're running the data center itself, is the racks and operationalizing what's inside those servers and running that, which I think that's a whole different challenge, and it's very deep. Requires very deep technological experts to make that stuff work properly.
Great, thank you, Mr. Russ. Ammar, I would like to address you now when it comes to the AI workloads and their extreme and rapid variations. So this would be creating a lot of strain on the electrical equipments within the data center. So I would like to know your point of view on how this is being dealt with from one side, and are the OEM R&Ds able to keep up with the pace of these new requirements that are happening?
Thank you, Homere. First of all, I would have to say that it's very tough position to be sitting between a consultant and an end user, and addressing such a question. But I'll try my best. So first of all, in terms of the challenges, I'm going to cover part of it, which is related to a macro scale. A macro scale, where I think, and maybe Ras can maybe relate to this more than because they are in the development stage of building more data centers. I think the biggest challenge right now is identifying the right location and getting the right power capacity. And when we talk about power capacity, we're not talking anymore about 1 megawatt and 10 megawatts. Right now, we're talking about multiple of hundreds or gigawatts. And developing this on a grid requires a lot of planning. Now, I was reading the other day that the average time to develop a high voltage substation is around 7 years when it comes to that size of data centers. So that doesn't align with that does not align at all with the plans that these data centers are being planned for. So that's on that is probably something that we as Eaton cannot maybe address. But from a power perspective, I would say, and supply chain perspective, this is the second biggest challenge that we are facing. How can we keep up with those hundreds of thousands of GPUs that are being built and being procured, and you need to build the infrastructure for those GPUs, right? While you cannot really produce, and the factories across the world, whether depends regardless of whose vendor and which equipment it is, whether generator, UPS, chiller, etc., they cannot keep up with this kind of demand. So obviously that's a second big challenge that everybody is facing: raw material, prices, logistics, and so on and so forth. And the third, I would say, probably more on the design aspect of it, where how can you predict what's going to come? Because now the issue is we are building for the GPUs of 100 and 200, and whether NVIDIA, AMD, whoever is producing these GPUs, we are designing and building the infrastructure as per what we have right now. And to George's point, right, if something change on the cooling side in terms of what kind of cooling you're using, what kind of pipes you're using, what kind of environment you are in, everything has to change, right? So. And it's all driven, unfortunately, not by us. It's driven by the chip manufacturer, as George also said, as rightly said. So we are more on the receiving end of it. So from the challenges, I would say these are the top three that I can think of. Now, what are we doing on it as OEMs? Obviously, we are in deep discussions with the likes of NVIDIAs and AMDs to develop the power, because we are in the power business, to develop the power solutions that are more relevant to their solution. So we're trying to play catch up with them, right? And it is progressing. I cannot say it's 100% there because obviously the technology keeps evolving, and to catch up, if the technology evolves every 2-3 years, your data center has to be there for like 15 to 20 years. That's the expectations, at least, right? So how can you build something from an infrastructure point of view that is resilient and that will stay there and that will predict the future of 15, 20 years? And I think that's the biggest challenge we are facing right now. Previously as well, we were looking at things more of, let's design that UPS or let's design that track or that PDU or that busway, etc. Right now, we're more looking at the entire powertrain. And I think this is what helps address the problem in a more macro scale rather than looking at just components level.
All right. So we're going to move on to Mr. Mark Stuart.
Thank you.
So with the liquid cooling practically being one of the main requirements for the chip manufacturers to cool them, and piping systems being actually what is going to transfer this cooling medium all the way from the CDUs mainly to the rack manifolds and so on. Has there been any development of actually an easy, fast, flexible, and reliable piping system that is able to optimize the cooling transfer from one side and the timeline of the project from the other side?
Yeah. Absolutely, and thanks for almost doing my job for me there, because reliability and speed was all part of it. Yeah, as GF piping systems, we've developed a suitable piping system for the TCS technical water, kind of based around our 35 years experience in the semiconductor market, where we have a partnership, global partnership with Intel, producing piping systems, reliable piping systems for the wafer chip manufacturing. So we're kind of going from in the manufacturing of the chips to now cooling the chips. So it kind of makes sense that we are using that experience. And we've developed products which are very fast to install, can be prefabricated, have a complete system, including the actual welding plants as well. So yeah, it's something that, from a George Fisher point of view, we continue to develop. And just thinking of the things that George said about maybe we get rid of the glycol. Well, with a full plastic system, you probably can get rid of the glycol. And I think, as we mentioned before, there's lots of pipes now. So the weight saving in a plastic piping system also makes a big difference. So yeah, so that's the kind of overview of where we are in the piping system at the moment.
Thank you, Mr. Mark. Mr. George, you would like to add something?
I just want to give you a takeaway what will happen. Today, data centers, let's say we have 100 megawatt. If we put 16 kilowatt rack, we need 100,000 square meter of white space and 50,000 square meter of utility and batteries. With the coming, let's say we went to 100 megawatt, 100 kilowatt rack, we will drop the 100,000 square meter down to 30,000 square meter. And the utility part will remain 50,000. So imagine how that will affect the building, the space requirement on a large scale. Just a small takeaway for you to think about.
We've seen that on our own sites where we've got a core and shell built and people think, oh, well, the core and shell is there, so that means you're almost there. It's like, no, the core and shell now is a very small part of this job. It's a tiny part. And, you know, getting the MEP delivered and installed and set up and configured and paid for is it's a huge burden. And, yeah.
Great. Gentlemen, I hope that we were useful for you today. Thank you, everyone, for joining this panel. I'm really happy we're having around 140 years of experience combined on this panel. Thank you for everyone for attending.
Thank you.